Welcome to our exploration of one of the most intriguing mysteries in the universe, the hidden realms of dark matter and dark energy within the cosmic microwave background. Imagine a universe where 85% of its mass is invisible, not emitting or absorbing light, yet its presence is felt through gravitational effects. This is dark matter, a crucial component of the cosmos that holds galaxies together. On the other hand, there's dark energy, an even more mysterious force driving the accelerated expansion of the universe, making up about 70% of its total energy density. To understand these cosmic phenomena, we turn to the cosmic microwave background, or CMB, the afterglow of the Big Bang that permeates the entire universe, offering a snapshot of the early universe. The CMB was discovered in 1965, and its uniformity and tiny fluctuations have provided a wealth of information about the universe's infancy, structure, and composition. Through precise measurements of the CMB, scientists can infer the influence of dark matter on the formation and distribution of galaxies, revealing patterns and anomalies that point to its presence. Similarly, the CMB helps us investigate dark energy by observing how it affects the universe's expansion rate, influencing the cosmic landscape over billions of years. Current theories like the LCDM model, or lambda-cold dark matter model, rely heavily on CMB data to describe a universe dominated by dark matter and dark energy, guiding our understanding and future research. Technological advancements, such as the Planck satellite, have enhanced our ability to measure the CMB with unprecedented precision, unveiling more details about these elusive components. As we delve deeper into these discoveries, we unravel the profound connection between dark matter, dark energy, and the CMB, pushing the boundaries of our knowledge and opening new avenues for exploration. In 1965, Arno Penzias and Robert Wilson stumbled upon the cosmic microwave background while working with a radio antenna. They were attempting to eliminate persistent noise from their data, but discovered the noise was uniform and came from all directions. This accidental discovery was monumental, providing the first direct evidence of the Big Bang. The CMB is essentially the afterglow of the universe's birth, stretched into microwave wavelengths by the expansion of the cosmos. Before this discovery, the Big Bang theory was one of several competing models explaining the universe's origin. The detection of the CMB, however, gave it a significant boost, solidifying it as the leading cosmological theory. The CMB is incredibly faint, yet it carries a wealth of information about the early universe. It represents the moment when the universe cooled enough for photons to travel freely, approximately 380,000 years after the Big Bang. This relic radiation is remarkably uniform, but contains slight variations in temperature. These tiny fluctuations, just a few microkelvin in difference, are crucial for understanding the universe's structure. The variations in the CMB reveal the seeds of all future cosmic structures, including galaxies and clusters of galaxies. They map out the density fluctuations present in the early universe. By studying these fluctuations, scientists can infer the conditions of the early universe and the processes that shaped its evolution. The CMB thus acts as a cosmic blueprint, detailing the universe's infancy. The detailed mapping of the CMB began with the Cosmic Background Explorer, COBE satellite in 1989. COBE's observations confirmed the CMB's blackbody spectrum and measured its temperature fluctuations, earning a Nobel Prize in physics. Following COBE, the Wilkinson Microwave Anisotropy Probe, WMAP, launched in 2001, providing even more precise measurements. WMAP's data refined our understanding of the universe's age, composition, and development. Most recently, the Planck satellite, launched in 2009, has offered the most detailed map of the CMB to date. Planck's observations have allowed for unprecedented precision in cosmological models, deepening our understanding of the universe. Each of these missions has progressively unveiled finer details of the CMB. They have helped cosmologists to pinpoint the universe's parameters, such as its age, rate of expansion, and content. The CMB's discovery and subsequent detailed study have been pivotal in transforming cosmology into a precise science. The data derived from the CMB has led to numerous breakthroughs in our understanding of the cosmos. By examining the CMB, we gain insights into not only the universe's past but also its present and future. The patterns observed in the CMB inform us about the fundamental forces and particles that govern the cosmos. The study of the CMB has also illuminated the roles of dark matter and dark energy. These invisible components influence the CMB's characteristics, allowing scientists to infer their properties and effects. As research continues, the CMB remains a critical tool for probing the mysteries of the universe. It offers a window into the earliest moments of creation and the underlying fabric of reality. The cosmic microwave background is a form of electromagnetic radiation that fills the universe. It is a remnant from an early stage in the development of the universe, also known as relic radiation. The CMB is remarkably uniform in all directions, with a temperature of about 2.7 Kelvin. This uniformity reflects the state of the universe when it became transparent, allowing photons to travel freely. Despite its overall uniformity, the CMB has tiny fluctuations in temperature. These variations are on the order of 1 part in 100,000 and are crucial for understanding the large-scale structure of the universe. These fluctuations in the CMB are known as anisotropies. They are the imprints of sound waves traveling through the early universe, providing insights into its density and composition. The CMB spectrum is that of a nearly perfect blackbody. This means it has a specific thermal radiation signature that matches the predictions of the Big Bang theory. Measuring the CMB's temperature and its fluctuations requires sensitive instruments. Satellites like COBE, WMAP, and Planck have been designed specifically to observe the CMB with high precision. The polarization of the CMB is another key property. This polarization arises from the scattering of photons off electrons when the universe was still young and can give additional information about the early universe. There are two types of polarization in the CMB: E modes and B modes. E modes are directly related to density fluctuations, while B modes can provide clues about gravitational waves in the early universe. The CMB also provides information about the curvature of the universe. Current observations suggest that the universe is flat, meaning it will continue to expand forever. Another important property is the integrated Sachs-Wolf effect. This occurs when photons travel through gravitational potential wells, leading to slight shifts in the CMB's temperature. The CMB's isotropy and the small-scale anisotropies provide a snapshot of the universe at the moment of recombination. This was the era when electrons and protons combined to form neutral hydrogen, making the universe transparent. The CMB also carries information about the universe's expansion rate. By studying the CMB, scientists can infer the Hubble constant, which measures the rate at which the universe is expanding. Analyzing the CMB helps us understand the distribution of dark matter. Dark matter influences the formation of structures in the universe, leaving detectable imprints on the CMB. The properties of the CMB are crucial for testing cosmological models. By comparing observations with theoretical predictions, scientists can refine their understanding of the universe's origins and evolution. In essence, the CMB acts as a cosmic blueprint. Its properties reveal the conditions of the early universe and continue to inform our understanding of the cosmos. Measuring the cosmic microwave background requires highly sensitive instruments. These instruments are typically placed on satellites, high-altitude balloons, or ground-based telescopes. The first major satellite to measure the CMB was the Cosmic Background Explorer, or COBE. Launched in 1989, COBE provided the first detailed measurements of the CMB's temperature and spectrum. COBE's instruments included a differential microwave radiometer. This device measured the temperature differences across the sky with great accuracy, confirming the CMB's uniformity and tiny fluctuations. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in 2001. WMAP improved upon COBE's measurements, providing higher resolution data and more precise mapping of the CMB. WMAP's mission lasted for 9 years, during which it collected data that helped refine the parameters of the standard cosmological model. Its findings provided insights into the universe's age, composition, and development. The Planck satellite, launched by the European Space Agency in 2009, offered even more detailed measurements. Planck's instruments were designed to measure the CMB with higher sensitivity and resolution than its predecessors. Planck used a combination of high-frequency and low-frequency instruments. These instruments covered a wide range of the electromagnetic spectrum, capturing detailed data about the CMB's temperature and polarization. Ground-based observatories like the Atacama Cosmology Telescope and the South Pole Telescope also contribute to CMB measurements. These telescopes operate at high altitudes to minimize atmospheric interference. High-altitude balloon experiments, such as the Boomerang experiment, have also provided valuable CMB data. These balloons carry instruments above most of the Earth's atmosphere, reducing signal distortion. To analyze the CMB, scientists use Fourier transforms. This mathematical technique helps separate the CMB signal from noise and other astrophysical sources, revealing the underlying patterns of temperature fluctuations. Instruments measuring the CMB must be cooled to very low temperatures. This cooling reduces thermal noise from the instruments themselves, ensuring the accuracy of the measurements. The data collected from these instruments is processed using sophisticated algorithms. These algorithms correct for various sources of error and produce maps of the CMB with unprecedented detail. Polarization measurements of the CMB require even more sensitive instruments. These measurements help scientists study the early universe's conditions, including the presence of gravitational waves. Each new generation of instruments builds on the success of previous missions. They provide more detailed and accurate data, enhancing our understanding of the universe's fundamental properties. The continuous improvement in CMB measurements is crucial for advancing cosmology. As technology progresses, future missions will likely provide even deeper insights into the cosmos. By measuring the CMB, we gain a clearer picture of the universe's origins, structure, and evolution. This ongoing research is key to answering fundamental questions about the nature of the cosmos. The cosmic microwave background holds immense significance in cosmology. It is the oldest light we can observe, providing a direct window into the early universe. By studying the CMB, cosmologists can trace the history of the universe back to its infancy. This radiation contains imprints of the conditions that prevailed just 380,000 years after the Big Bang. The uniformity of the CMB supports the Big Bang theory, offering strong evidence that the universe began from a hot, dense state. This finding has helped to shape our understanding of cosmic evolution. The tiny fluctuations in the CMB are crucial for explaining the large-scale structure of the universe. These fluctuations represent the seeds from which galaxies and clusters of galaxies eventually formed. Analyzing the CMB helps determine fundamental cosmological parameters. Parameters such as the universe's age, the Hubble constant, and the density of various components are derived from CMB observations. The CMB also provides insights into the composition of the universe. It reveals the proportions of dark matter, dark energy, and ordinary matter, helping to refine the standard model of cosmology. The study of the CMB has led to the development of the LCDM model, or Lambda Cold Dark Matter model. This model describes a universe dominated by dark energy and dark matter, with ordinary matter making up a small fraction. The polarization of the CMB offers additional information. It helps cosmologists understand the ionization history of the universe and the influence of primordial gravitational waves. The CMB's anisotropies are linked to the early universe's density fluctuations. These fluctuations inform us about the physics of the very early universe, including the process of inflation. The integrated Sachs-Wolf effect observed in the CMB helps measure the influence of dark energy. This effect shows how the CMB photons gain energy when passing through evolving gravitational potential wells. By comparing CMB data with large-scale structure surveys, scientists can test theories of cosmic evolution. These comparisons help validate or challenge current models, driving the advancement of cosmology. The CMB is a cornerstone for the theory of cosmic inflation. Inflation proposes a rapid expansion of the universe fractions of a second after the Big Bang, and the CMB carries potential evidence of this event. Understanding the CMB's properties enables predictions about the universe's fate. It informs us about how the universe might continue to expand and evolve over billions of years. The precise measurements of the CMB have transformed cosmology into a precision science. They provide benchmarks against which other astronomical observations are compared and interpreted. The ongoing study of the CMB continues to uncover new insights. Each discovery enriches our knowledge of the universe and helps answer fundamental questions about its origin, structure, and destiny. The cosmic microwave background is a cornerstone of the Big Bang theory. It serves as the afterglow of the universe's birth, providing a snapshot of the cosmos at its earliest stages. According to the Big Bang theory, the universe began as a hot, dense singularity. As it expanded, it cooled, leading to the formation of atoms and eventually allowing photons to travel freely, creating the CMB. The uniformity of the CMB across the sky supports the idea of a homogeneous and isotropic universe at large scales. This aligns with the predictions made by the Big Bang model. The tiny temperature fluctuations observed in the CMB are remnants of sound waves from the early universe. These fluctuations are key evidence of the density variations that would eventually lead to galaxy formation. The CMB spectrum is a nearly perfect blackbody, matching the predictions of the Big Bang theory. This blackbody spectrum indicates that the universe was once in a state of thermal equilibrium. The discovery of the CMB provided the first direct evidence for the Big Bang theory. Before this discovery, the Big Bang was just one of several competing theories about the universe's origin. The CMB's properties allow scientists to estimate the age of the universe. By analyzing the CMB, they can determine that the universe is approximately 13.8 billion years old. The CMB also offers insights into the early stages of cosmic inflation. This rapid expansion shortly after the Big Bang is thought to have smoothed out the universe and created the initial fluctuations observed in the CMB. Observations of the CMB help refine our understanding of the universe's composition. They reveal the relative amounts of dark matter, dark energy, and ordinary matter, all of which were influenced by the conditions just after the Big Bang. The Sachs-Wolf effect, seen in the CMB, provides evidence for the gravitational redshift of photons. This effect occurs because of the changing gravitational potential as the universe expands, supporting the Big Bang framework. The polarization patterns in the CMB give clues about the ionization history of the universe. These patterns align with the Big Bang theory's predictions about how the first atoms formed and the universe became transparent. The CMB allows scientists to test and refine the Big Bang model. Each new measurement and observation helps confirm the theory's predictions or prompts adjustments to our understanding. The success of the Big Bang theory in explaining the CMB's properties has made it the prevailing cosmological model. Competing theories have struggled to match the empirical data provided by the CMB. The consistency of CMB data with the Big Bang model has led to widespread acceptance among scientists. It serves as a foundation for understanding the universe's past, present, and future. The link between the CMB and the Big Bang theory underscores the importance of continued CMB research. Each new discovery about the CMB helps us better understand the origins and evolution of the universe. Dark matter's existence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the earliest clues came from observing the rotation curves of galaxies. In spiral galaxies, the outer stars rotate much faster than expected based on visible matter alone. This discrepancy suggests the presence of an unseen mass, now known as dark matter. Galaxy clusters provide another piece of evidence. The gravitational pull needed to hold these clusters together is far greater than what can be accounted for by visible matter alone. Gravitational lensing is a phenomenon where light from distant objects is bent by the gravity of massive objects like galaxy clusters. The degree of lensing observed indicates more mass than what we can see. The cosmic microwave background itself offers clues about dark matter. The patterns of temperature fluctuations in the CMB are influenced by the presence of dark matter in the early universe. Large-scale simulations of the universe's evolution require dark matter to match observations. Without dark matter, these models fail to produce structures like galaxies and clusters in the way we see them today. Dark matter also plays a crucial role in the formation of galaxies. Its gravitational pull helps gas clouds collapse and form stars, influencing the overall structure of galaxies. Observations of the Bullet cluster provide direct evidence of dark matter. In this collision of two galaxy clusters, the visible matter and dark matter separate, revealing the latter through gravitational lensing. Dark matter does not interact with electromagnetic forces, making it invisible and detectable only through its gravitational effects. This property differentiates it from ordinary matter, which interacts with light. The distribution of dark matter in the universe affects the movement of galaxies within clusters. These movements suggest much more mass than can be seen, consistent with dark matter's presence. Studies of the cosmic web, the large-scale structure of the universe, indicate dark matter's influence. The way galaxies are distributed along filamentary structures aligns with predictions involving dark matter. The behavior of hot gas in galaxy clusters also points to dark matter. The temperature and distribution of this gas, as revealed by X-ray observations, require additional mass to explain. Dark matter's gravitational effects help us understand the dynamics of galaxies and clusters. Without dark matter, the observed speeds and distributions of these objects cannot be adequately explained. Direct detection experiments aim to identify dark matter particles by observing their interactions with regular matter. While results are still pending, these experiments are crucial for confirming dark matter's nature. As our understanding of dark matter grows, it continues to be a vital component of cosmological models. Its evidence, while indirect, is compelling and essential for explaining many astronomical phenomena. Dark matter plays a fundamental role in galaxy formation. Its gravitational influence helps pull together gas and dust to form the first stars and galaxies. Without dark matter, the gas in the early universe would not have had enough gravitational pull to collapse and form stars. Dark matter's extra mass provided the necessary force for these structures to coalesce. The distribution of dark matter in the universe creates potential wells where galaxies can form. These wells are regions of higher density that attract baryonic matter, the ordinary matter that makes up stars and planets. As dark matter clumps together through gravitational attraction, it creates the scaffolding for galaxies. These clumps grow over time, pulling in more gas and forming larger structures. Simulations of the early universe show that dark matter is essential for forming the filamentary structures we observe. These filaments are the cosmic web, with galaxies forming along these dark matter strands. Dark matter halos surround galaxies, providing additional gravitational support. These halos help maintain the rotation speeds of galaxies, explaining why stars in the outer regions do not fly away. Observations of galaxy clusters show that dark matter's presence is crucial for holding these massive structures together. The visible mass alone is insufficient to account for the gravitational binding of these clusters. During galaxy mergers, dark matter plays a key role in the dynamics of the interaction. Its gravitational influence affects how galaxies merge and the resulting shapes of the merged galaxies. The process of cooling and compressing gas within dark matter halos leads to star formation. As gas falls into these halos, it heats up, cools down, and eventually forms new stars. Dark matter also impacts the rate of star formation in galaxies. By providing the necessary gravitational pull, it regulates the amount of gas available for star formation. The formation of disk galaxies, like our Milky Way, is influenced by dark matter. The dark matter halo helps stabilize the galaxy, allowing the disk to form and persist. Elliptical galaxies, often found in dense environments, also rely on dark matter for their formation. The interactions and mergers in these regions are driven by the underlying dark matter distribution. Dwarf galaxies, which are small and faint, are heavily dominated by dark matter. Their existence and survival in the universe are largely due to the protective influence of dark matter. The study of dark matter-rich galaxies provides insights into galaxy formation and evolution. These galaxies help astronomers understand how dark matter influences different types of galaxies. Dark matter continues to shape galaxies throughout their lifetimes. Its ongoing gravitational effects influence the behavior and structure of galaxies over billions of years. Dark matter remains one of the biggest mysteries in cosmology. Scientists have proposed several candidates that might explain this elusive substance. One leading candidate is weakly interacting massive particles, or WIMPs. These hypothetical particles interact through gravity and possibly the weak nuclear force, but not with electromagnetic forces. WIMPs are predicted by extensions of the standard model of particle physics, such as supersymmetry. If WIMPs exist, they would be abundant and massive enough to account for dark matter's gravitational effects. Another candidate is axions, which are very light and interact extremely weakly with normal matter. Axions were originally proposed to solve a problem in quantum chromodynamics, a theory describing strong nuclear interactions. Sterile neutrinos are another possible dark matter candidate. Unlike the known active neutrinos, sterile neutrinos do not interact through the weak nuclear force, making them difficult to detect. Primordial black holes are a more exotic candidate. These black holes would have formed in the early universe and could account for some or all of the dark matter, though their existence remains speculative. Dark matter could also consist of massive astrophysical compact halo objects, or MACHOs. These include objects like black holes, neutron stars, and brown dwarfs that are not easily detectable by their emitted light. A more recent idea involves dark photons, which would be a dark sector analog of ordinary photons. Dark photons could interact with dark matter particles, potentially explaining some observations. Self-interacting dark matter is another concept where dark matter particles interact with each other through a new force. This could help explain certain galaxy cluster behaviors that standard cold dark matter models struggle with. The concept of superfluid dark matter combines ideas from condensed matter physics with cosmology. In this scenario, dark matter exhibits superfluid properties on cosmic scales, affecting galaxy dynamics. Some theories propose that dark matter could be composed of ultralight bosons. These particles, with masses far below that of WIMPs, could form wave-like structures on galactic scales. Composite dark matter suggests that dark matter particles might be made up of more fundamental components. These composite particles could have complex interactions, unlike simpler WIMPs or axions. Hidden sector theories posit that dark matter resides in a separate sector of particles and forces. These hidden particles would interact weakly with those in the visible sector, making them difficult to detect directly. Dark matter may also come from modifications to gravity itself, such as theories involving extra dimensions. These theories propose that what we perceive as dark matter could be a manifestation of altered gravitational laws. Ongoing experiments and observations aim to detect these candidates. Projects like the Large Hadron Collider, direct detection experiments, and astrophysical surveys all contribute to this effort. The search for dark matter candidates is crucial for understanding the universe's fundamental nature. Each potential candidate brings us closer to solving this cosmic puzzle. Detecting dark matter is one of the greatest challenges in modern physics. Researchers employ a variety of methods to uncover these elusive particles. Direct detection experiments aim to observe dark matter particles interacting with ordinary matter. These experiments are typically conducted deep underground to shield them from cosmic rays. One common technique involves using large tanks of liquid xenon or argon. When a dark matter particle collides with an atom in the liquid, it produces a small flash of light and free electrons, which can be detected. Cryogenic detectors operate at extremely low temperatures, using crystals like germanium or silicon. These detectors measure the tiny vibrations caused by dark matter particles hitting atomic nuclei. Another approach is indirect detection, which searches for the byproducts of dark matter annihilations or decays. When dark matter particles collide, they can produce gamma rays, neutrinos, or other particles. Gamma-ray telescopes like the Fermi Gamma-ray Space Telescope look for excess gamma rays from regions with high dark matter density. The galactic center is a prime target due to its expected abundance of dark matter. Neutrino detectors, such as IceCube at the South Pole, search for neutrinos that might be produced by dark matter interactions. These detectors can identify high-energy neutrinos from space. Positron and antiproton excesses in cosmic rays might also indicate dark matter. Experiments like AMS-02 on the International Space Station measure these cosmic rays with high precision. Another method involves gravitational lensing, where dark matter bends light from distant objects. By studying these lensing effects, scientists can map the distribution of dark matter in galaxies and clusters. The motion of stars and gas within galaxies provides clues about dark matter's presence. Rotational curves of galaxies reveal discrepancies that suggest the influence of dark matter. Particle colliders like the Large Hadron Collider search for dark matter by recreating high-energy conditions, similar to those just after the Big Bang. These experiments look for missing energy and momentum that could indicate dark matter particles. Simulations of the universe's structure formation also help in understanding dark matter. By comparing these simulations with actual observations, researchers can test different dark matter models. Axion detectors use resonant cavities or magnetic fields to convert axions into detectable photons. Experiments like ADMX are designed specifically to search for these hypothetical particles. Sterile neutrino searches focus on detecting X-rays produced by their decay. Satellites like XMM Newton and Chandra look for unexplained X-ray emissions that could signal sterile neutrinos. Advanced theoretical models guide these detection efforts. They help scientists refine their search parameters and interpret potential signals from dark matter interactions. Each detection method contributes to a comprehensive search strategy. By combining multiple approaches, scientists hope to finally uncover the true nature of dark matter. Dark matter research faces numerous challenges due to its elusive nature. One major hurdle is that dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopes. Detecting dark matter directly is incredibly difficult because it interacts very weakly with ordinary matter. This weak interaction requires highly sensitive detectors and environments free from background noise. Background radiation and cosmic rays can easily mimic or obscure potential dark matter signals. To mitigate this, experiments are conducted deep underground or in isolated locations. Even with these precautions, distinguishing a true dark matter signal from noise is complex. Scientists must develop sophisticated data analysis techniques to identify potential dark matter interactions. Another challenge is the wide range of possible dark matter candidates. Each candidate, from WIMPs to axions, requires different detection methods and technologies, complicating the search. Theoretical models of dark matter need constant refinement. As new data emerges, these models must be updated to accurately predict the properties and behaviors of dark matter particles. High-energy particle colliders like the Large Hadron Collider have yet to produce definitive evidence of dark matter. This absence of direct detection suggests that dark matter might be more elusive than current models predict. Astrophysical observations such as gravitational lensing and galaxy rotation curves provide indirect evidence of dark matter. However, these methods cannot identify the specific particles that make up dark matter. The vast parameter space for dark matter properties, such as mass and interaction strength, is another obstacle. Researchers must explore a wide range of possibilities, requiring extensive resources and time. Experiments searching for dark matter often face funding and logistical challenges. Building and maintaining highly sensitive detectors is costly and requires long-term investment. Interdisciplinary collaboration is essential in dark matter research, but coordinating efforts across different fields and institutions can be difficult. Effective communication and data sharing are crucial for progress. Theoretical predictions about dark matter often rely on assumptions that may not hold true. If these assumptions are incorrect, it could lead researchers down the wrong path, wasting valuable time and resources. Even if a potential dark matter signal is detected, confirming its nature is challenging. Multiple lines of evidence and reproducibility are necessary to validate any discovery. The potential for false positives or unaccounted for background events is high. Researchers must carefully design experiments to minimize these risks and thoroughly analyze all data. Despite these challenges, the pursuit of dark matter remains a top priority in physics and cosmology. Each step forward, no matter how small, brings us closer to understanding this fundamental component of the universe. Dark energy's existence is inferred from its effects on the expansion of the universe. The first major evidence came from observing distant supernovae. In the late 1990s, two independent teams studying Type Ia supernovae discovered that these exploding stars were dimmer than expected. This indicated that the universe's expansion is accelerating, suggesting the presence of dark energy. The cosmic microwave background provides additional evidence for dark energy. Precise measurements of the CMB show patterns consistent with a universe dominated by dark energy. The large-scale structure of the universe also hints at dark energy. Surveys of galaxy distribution reveal a pattern of clustering that aligns with models including dark energy. Gravitational lensing studies support the existence of dark energy. By observing how light bends around massive objects, scientists can infer the influence of dark energy on the universe's geometry. The integrated Sachs-Wolf effect is another piece of evidence. This phenomenon involves CMB photons gaining energy when passing through evolving gravitational potential wells, which dark energy affects. Baryon acoustic oscillations, remnants of sound waves in the early universe, provide a standard ruler for measuring cosmic distances. Their observed scale matches predictions that include dark energy. The relationship between the age of the universe and the Hubble constant further supports dark energy. Models without dark energy cannot adequately explain the observed rate of expansion and the universe's age. Clusters of galaxies also offer clues about dark energy. The growth rate of these clusters over time aligns with the influence of dark energy in slowing down the growth of cosmic structures. Observations of the universe's flatness suggest dark energy. The combined data from the CMB, galaxy surveys, and supernovae point to a universe that is geometrically flat, requiring a significant amount of dark energy. The behavior of the cosmic microwave background's polarization provides indirect evidence for dark energy. Patterns in the polarization help trace the universe's expansion history, which dark energy influences. Dark energy's presence affects the universe's overall energy budget. Observations show that approximately 70% of the universe's energy density is attributed to dark energy. Cosmological simulations that include dark energy match observed structures and dynamics of the universe more accurately than those without it. This consistency supports the concept of dark energy. Theoretical models like the cosmological constant, L, describe dark energy as a constant energy density filling space. These models align well with current observations of cosmic acceleration. Despite being elusive and not directly observable, the cumulative evidence from various astronomical observations strongly supports the existence of dark energy, shaping our understanding of the cosmos. Dark energy has a profound impact on the expansion of the universe. It drives the accelerated expansion we observe today, affecting the fate of the cosmos. Initially, the universe's expansion was decelerating due to gravitational attraction. However, dark energy's repulsive force overcame this, leading to acceleration. This accelerated expansion means that galaxies are moving away from each other at increasing speeds. Over time, this will result in galaxies becoming more isolated. And the Hubble constant measures the current rate of expansion. Observations indicate that this rate is increasing, consistent with the influence of dark energy. Dark energy affects the growth of cosmic structures. It counteracts gravitational attraction, slowing down the formation of large-scale structures like galaxy clusters. In a dark energy-dominated universe, the expansion rate will continue to accelerate. This has significant implications for the future of cosmic evolution. The accelerated expansion changes our understanding of the universe's age. With dark energy, the universe is older than previously thought when only deceleration was considered. Cosmological models incorporating dark energy predict a future where galaxies move beyond the observable horizon. This would make them undetectable to future astronomers. The concept of the cosmic event horizon arises from accelerated expansion. It defines a boundary beyond which events cannot affect an observer, influenced by dark energy. Dark energy also impacts the cosmic microwave background. The patterns in the CMB provide evidence of the universe's changing expansion rate due to dark energy. The integrated Sachs-Wolf effect observed in the CMB is directly related to dark energy. It demonstrates how dark energy influences the gravitational potential over time. The presence of dark energy necessitates modifications to general relativity. It introduces the cosmological constant or other forms of dark energy into Einstein's equations. The nature of dark energy remains one of the biggest mysteries in cosmology. Understanding its properties could reveal new physics beyond our current theories. Dark energy's influence extends to the fate of the universe. Depending on its properties, it could lead to scenarios like the Big Freeze, Big Rip, or a stable expansion. Research into dark energy continues to be a top priority in cosmology. Unraveling its nature will provide deeper insights into the fundamental workings of the universe. The cosmological constant is a term introduced by Einstein in his equations of general relativity. Originally, Einstein added it to achieve a static universe, but later it was seen as a form of dark energy. The cosmological constant represents a constant energy density filling space homogeneously. This energy has a repulsive effect, driving the accelerated expansion of the universe. In the context of modern cosmology, the cosmological constant is denoted by the symbol lambda, or L. It is a key component of the lambda cold dark matter model, the standard model of cosmology. The value of the cosmological constant is extremely small, yet it dominates the energy density of the universe. This small value is what causes the gentle, yet accelerating expansion. One mystery of the cosmological constant is why its value is so small compared to theoretical predictions. This discrepancy is known as the cosmological constant problem. Quantum field theory predicts a much larger value for the vacuum energy, which is associated with the cosmological constant. The actual value observed is many orders of magnitude smaller. This disparity between theory and observation is a major puzzle in theoretical physics. It suggests that our understanding of vacuum energy and dark energy is incomplete. Despite this, the cosmological constant effectively explains many observed phenomena. It accounts for the accelerated expansion and fits well with data from supernovae, the cosmic microwave background, and galaxy distributions. The cosmological constant is considered a form of dark energy because it has a uniform, repulsive force. This force works against gravity, influencing the large-scale dynamics of the universe. Its presence affects the geometry of the universe, making it flat or nearly flat. This flatness has been confirmed by measurements of the cosmic microwave background. The concept of the cosmological constant is simple, yet profound. It introduces a constant energy component that has far-reaching implications for cosmology and theoretical physics. Some theories suggest that the cosmological constant might change over time. These theories propose dynamic forms of dark energy, such as quintessence, where the energy density varies. However, current observations are consistent with a constant value for L. This simplicity makes the cosmological constant a convenient and effective explanation for dark energy. Understanding the true nature of the cosmological constant could unlock deeper insights into the universe. It connects to fundamental questions about the nature of space, time, and energy. As research continues, the cosmological constant remains a central topic in the quest to understand the universe. Its implications stretch across cosmology, particle physics, and beyond. Alternative theories to the cosmological constant seek to explain dark energy in different ways. One prominent theory is quintessence, which posits a dynamic form of dark energy that changes over time. Quintessence involves a scalar field that evolves as the universe expands. Unlike the cosmological constant, its energy density is not fixed and can vary, affecting the rate of cosmic acceleration. Another idea is modified gravity, which suggests that the laws of gravity themselves may need adjustment. These theories propose changes to general relativity to account for dark energy effects. One example of modified gravity is FR gravity, where the gravitational Lagrangian is a function of the Ricci scalar, R. This modification can lead to accelerated expansion without invoking dark energy. Another approach is brain-world models, which posit extra dimensions beyond the familiar 3 of space and 1 of time. In these models, our universe is a brain within a higher dimensional space, and gravity leaks into these extra dimensions. The chameleon theory proposes that dark energy's properties change depending on the local environment. It behaves differently in regions of varying matter density, providing a mechanism for varying cosmic acceleration. K-essence is another scalar field theory similar to quintessence, but with non-standard kinetic terms. This allows for a wide range of dynamic behaviors and interactions with matter. Phantom energy theories suggest dark energy with an equation of state parameter less than -1. This implies even more rapid acceleration, potentially leading to a future Big Rip scenario where the universe tears apart. Interacting dark energy models explore the idea that dark energy and dark matter might interact. This interaction could influence the evolution of the universe and the growth of cosmic structures. Holographic dark energy theories are based on principles from quantum gravity and string theory. They propose that the dark energy density is related to the observable horizon of the universe. Cardassian expansion models suggest that modifications to the Friedmann equations can account for dark energy effects. These models alter the relationship between matter, energy, and the universe's expansion. Theories involving cosmic fluids propose that dark energy arises from unconventional forms of matter. These fluids have unusual properties that lead to repulsive gravitational effects. Another intriguing idea is vacuum metamorphosis, where a phase transition in the vacuum energy could cause the observed acceleration. This transition could occur at different epochs in cosmic history. Some theories suggest that what we perceive as dark energy might be the result of large-scale inhomogeneities. These inhomogeneities could affect our measurements and interpretations of cosmic acceleration. Exploring these alternative theories helps expand our understanding of dark energy. Each theory offers unique insights and predictions, guiding observations and experiments in the quest to understand the universe's accelerating expansion. Current research on dark matter and dark energy is rapidly advancing. Scientists are using a combination of observational data, theoretical models, and simulations to understand these mysterious components of the universe. One major focus is on refining measurements of the cosmic microwave background. Projects like the Planck satellite and future missions aim to provide even more detailed maps of the CMB's fluctuations and polarization. Surveys of large-scale structures, such as the Sloan Digital Sky Survey, are mapping the distribution of galaxies and dark matter. These surveys help reveal the underlying structure of the universe and the influence of dark energy on its expansion. Gravitational lensing studies are becoming increasingly precise. Instruments like the Dark Energy Survey are measuring how light from distant galaxies is bent by dark matter, providing insights into its distribution and properties. Particle physics experiments are also crucial. The Large Hadron Collider continues to search for new particles that could be dark matter candidates, such as WIMPs or axions. Direct detection experiments like the Xenon 1T and Lux Zeppelin detectors are searching for dark matter interactions with ordinary matter. These experiments aim to catch rare collisions between dark matter particles and nuclei. Neutrino observatories, including IceCube and Super Kamiokande, are looking for high-energy neutrinos that might result from dark matter annihilations or decays. These observations could provide indirect evidence for dark matter. Astronomers are also studying supernovae to measure the universe's expansion rate more accurately. The discovery of new distant supernovae helps refine estimates of the Hubble constant and dark energy's effects. The Euclid mission, set to launch in the near future, will map the geometry of the dark universe. By observing billions of galaxies, it will help determine the nature of dark energy and its impact on cosmic acceleration. The James Webb Space Telescope will provide unprecedented views of the early universe. Its observations could reveal how dark matter influenced the formation of the first galaxies and stars. Theoretical physicists are developing new models to explain dark energy and dark matter. These models explore various possibilities, from modifications to general relativity to entirely new particles and forces. Simulations of cosmic evolution are becoming more sophisticated. By comparing these simulations with observational data, researchers can test different hypotheses about dark matter and dark energy. Machine learning and artificial intelligence are being used to analyze vast amounts of cosmological data. These tools help identify patterns and correlations that might be missed by traditional analysis methods. Collaborations between different research fields are essential. Astrophysicists, particle physicists, and cosmologists are working together to piece together the puzzle of dark matter and dark energy. New technologies and instruments are constantly being developed. These advancements enable more precise measurements and open new avenues for exploration. As our understanding of dark matter and dark energy grows, each discovery brings us closer to solving some of the universe's most profound mysteries. The ongoing research is a testament to human curiosity and the quest for knowledge. Anisotropies in the cosmic microwave background are tiny variations in temperature. These variations are on the order of 1 part in 100,000 and provide a wealth of information about the early universe. These anisotropies were first detected by the COBE satellite in 1992. They were later mapped in greater detail by the WMAP and Planck missions. The anisotropies are not random but show a specific pattern. This pattern reflects the density fluctuations in the early universe, which eventually led to the formation of galaxies and clusters. These temperature fluctuations arise from sound waves traveling through the hot plasma of the early universe. The peaks and troughs of these waves correspond to regions of slightly different densities. The detailed study of these anisotropies helps cosmologists determine key parameters of the universe. These include the age, composition, and rate of expansion of the universe. By analyzing the anisotropies, scientists can measure the density of dark matter and dark energy. These measurements are crucial for understanding the overall structure and fate of the universe. The anisotropies also provide evidence for the theory of cosmic inflation. Inflation predicts a rapid expansion of the universe fractions of a second after the Big Bang, leaving imprints on the CMB. One significant feature observed in the anisotropies is the acoustic peaks. These peaks correspond to the scales of the sound waves and provide information about the universe's geometry and contents. And the position and height of these peaks depend on the total amount of matter and energy in the universe. Comparing observations with theoretical models helps refine our understanding of these components. Polarization patterns in the CMB anisotropies offer additional insights. These patterns are caused by the scattering of photons off electrons and provide information about the ionization history of the universe. The E-mode polarization pattern is directly related to the density fluctuations. It helps to improve the precision of measurements of cosmological parameters. The B-mode polarization pattern is much weaker, but holds clues about gravitational waves from the early universe. Detecting these patterns is a major goal for future CMB experiments. The study of CMB anisotropies has led to several important discoveries. It has confirmed the Big Bang model, provided evidence for dark matter and dark energy, and supported the theory of inflation. Each new measurement of the CMB anisotropies helps to refine our cosmological models. These measurements are crucial for understanding the universe's origins, structure, and evolution. The ongoing analysis of anisotropies in the CMB remains a central focus of cosmological research. It continues to provide valuable insights into the fundamental properties of the universe. Dark matter has a significant influence on the cosmic microwave background. Its gravitational effects are imprinted in the anisotropies observed in the CMB. The presence of dark matter affects the density fluctuations in the early universe. These fluctuations create the initial conditions for the formation of galaxies and large-scale structures. Dark matter does not interact with light directly, but affects the distribution of ordinary matter. This interaction shapes the acoustic peaks observed in the CMB. The gravitational pull of dark matter creates potential wells. These wells influence how sound waves propagate through the early universe's plasma. These sound waves are visible in the CMB as temperature fluctuations. The detailed pattern of these fluctuations reveals the amount and distribution of dark matter. The height and position of the acoustic peaks in the CMB spectrum provide clues about dark matter. By studying these peaks, scientists can estimate the dark matter density. Dark matter's influence helps to determine the overall geometry of the universe. Observations show that the universe is flat, which is consistent with the presence of dark matter. The integrated Sachs-Wolf effect is another way dark matter impacts the CMB. This effect occurs when CMB photons pass through evolving gravitational potentials, influenced by dark matter. By analyzing the integrated Sachs-Wolf effect, scientists can gain insights into the interaction between dark matter and dark energy. This interaction helps to explain the accelerated expansion of the universe. The distribution of dark matter also affects the polarization of the CMB. Studying the E-mode and B-mode polarizations provides further information about dark matter's role in cosmic history. Dark matter clumps create gravitational lensing effects on the CMB. These effects distort the CMB patterns, offering additional ways to study dark matter distribution. Gravitational lensing by dark matter helps refine measurements of cosmological parameters. It adds another layer of precision to our understanding of the universe's composition. Numerical simulations that include dark matter match the observed CMB anisotropies. These simulations validate our models and improve predictions about the universe's evolution. The study of dark matter's influence on the CMB bridges the gap between particle physics and cosmology. It helps to connect the behavior of fundamental particles with large-scale cosmic structures. Ongoing research continues to explore the detailed impact of dark matter on the CMB. Each new finding helps to deepen our understanding of this invisible but crucial component of the universe. Observations and experiments play a crucial role in understanding the cosmic microwave background and its relation to dark matter and dark energy. The COBE satellite, launched in 1989, was a pioneering mission that provided the first detailed measurements of the CMB. Following COBE, the Wilkinson Microwave Anisotropy Probe, or WMAP, was launched in 2001. WMAP significantly improved the resolution of CMB measurements, offering more precise data about the universe's age and composition. The Planck satellite, launched in 2009, provided the most detailed map of the CMB to date. Planck's observations have been instrumental in refining the parameters of the standard cosmological model. Ground-based observatories, such as the Atacama Cosmology Telescope and the South Pole Telescope, complement space missions. These telescopes provide high-resolution measurements of the CMB's small-scale features. Balloon-borne experiments like Boomerang and EBEX offer another method of studying the CMB. These experiments fly above most of the Earth's atmosphere, reducing interference and enhancing measurement accuracy. Gravitational lensing studies using instruments like the Dark Energy Survey map how light is bent by dark matter. This technique helps reveal the distribution and properties of dark matter. Neutrino observatories such as IceCube search for high-energy neutrinos that could result from dark matter interactions. These observations provide indirect evidence of dark matter's presence. Direct detection experiments like Xenon 1T and Lux Zeppelin aim to observe dark matter particles interacting with ordinary matter. These experiments are conducted deep underground to shield them from cosmic rays and other background noise. Particle colliders, including the Large Hadron Collider, search for new particles that could be dark matter candidates. These experiments recreate the high-energy conditions of the early universe. Surveys of large-scale structures, such as the Sloan Digital Sky Survey, map the distribution of galaxies and dark matter. These surveys help us understand the influence of dark energy on cosmic expansion. The Euclid mission, set to launch soon, will map the dark universe with unprecedented precision. It will observe billions of galaxies to study dark energy's effects on the universe's acceleration. The James Webb Space Telescope will observe the early universe, providing insights into the formation of the first galaxies and stars. Its findings will help us understand how dark matter influenced these processes. Polarization measurements of the CMB, using instruments like the Polar Bear experiment, provide additional data about the early universe. These measurements help study the ionization history and the influence of gravitational waves. Theoretical models are constantly being refined based on observational data. These models explore various hypotheses about dark matter and dark energy, guiding future experiments. Continued observations and experiments are essential for advancing our understanding of the universe. Each new discovery adds to our knowledge, helping to solve the mysteries of dark matter and dark energy. One key finding from CMB studies is the confirmation of the Big Bang theory. The uniformity and slight variations in the CMB align with predictions from this model. The precise measurements of the CMB have allowed scientists to determine the age of the universe. Current estimates place it at approximately 13.8 billion years old. Observations of the CMB have provided strong evidence for the existence of dark matter. The patterns and distributions seen in the CMB cannot be explained by visible matter alone. The CMB data has revealed that dark energy makes up about 70% of the universe's total energy density. This discovery has profound implications for our understanding of the universe's expansion. The detection of acoustic peaks in the CMB has offered insights into the universe's composition. These peaks confirm the presence of dark matter and ordinary matter in specific proportions. The anisotropies in the CMB have provided evidence for cosmic inflation. This rapid expansion in the early universe is necessary to explain the observed uniformity of the CMB. Measurements of the CMB's polarization have enhanced our understanding of the Rayonization era. This period, when the first stars and galaxies formed, left distinct imprints on the CMB. The integrated Sachs-Wolf effect observed in the CMB supports the existence of dark energy. This effect shows how the universe's expansion rate changes over time due to dark energy. Gravitational lensing effects seen in the CMB help map the distribution of dark matter. These observations are crucial for understanding the structure and evolution of the universe. The precise mapping of the CMB has helped confirm the flat geometry of the universe. This finding is consistent with the predictions of the standard cosmological model. The study of the CMB has refined the value of the Hubble constant, which measures the universe's expansion rate. This value is critical for understanding the universe's past and future. CMB data has revealed the presence of neutrinos in the early universe. These light particles influenced the formation of large-scale structures and left imprints on the CMB. The findings from the Planck satellite have provided the most detailed picture of the early universe. This data has been instrumental in testing and refining cosmological models. The consistency of CMB observations with theoretical predictions has strengthened the standard model of cosmology. This model describes a universe dominated by dark energy and dark matter. Each key finding from CMB research brings us closer to understanding the fundamental nature of the universe. The ongoing analysis of this ancient light continues to shed light on the cosmos' deepest mysteries. Future research will focus on even more precise measurements of the cosmic microwave background. Upcoming missions aim to capture finer details of its temperature fluctuations and polarization. The European Space Agency's Euclid mission will map the geometry of the dark universe with unprecedented precision. This mission will provide new insights into dark energy and its effects on cosmic acceleration. The James Webb Space Telescope will explore the formation of the first galaxies and stars. Its observations will shed light on how dark matter influenced these early cosmic structures. Ground-based observatories like the Simons Observatory are set to improve our understanding of the CMB. These observatories will provide high-resolution images of the CMB's small-scale features. Balloon-borne experiments will continue to play a crucial role. Missions like the upcoming Spider and Piper will focus on measuring the polarization of the CMB to detect gravitational waves from inflation. Researchers are developing new techniques for direct detection of dark matter. These include more sensitive detectors and innovative approaches to isolate potential dark matter signals. Particle physics experiments will search for new particles that could be dark matter candidates. These experiments aim to recreate conditions similar to those just after the Big Bang. Astrophysical surveys will map the distribution of galaxies with greater accuracy. These surveys will help to understand the influence of dark energy on the universe's large-scale structure. Advanced simulations of the universe's evolution will become increasingly detailed. By comparing these simulations with observational data, scientists can test and refine different dark matter and dark energy models. Collaborations between different research fields will intensify. Astrophysicists, particle physicists, and cosmologists will work together to solve the mysteries of dark matter and dark energy. Machine learning and artificial intelligence will be employed to analyze vast amounts of cosmological data. These tools will help identify patterns and make predictions that might be missed by traditional methods. Future gravitational lensing studies will provide deeper insights into dark matter distribution. Enhanced lensing maps will reveal more about the universe's structure and evolution. Neutrino observatories will search for high-energy neutrinos that could result from dark matter interactions. These observations could offer indirect evidence of dark matter's presence. Theoretical research will explore new models of dark energy and dark matter. Scientists will investigate novel hypotheses and their implications for cosmology. International collaborations will be crucial for advancing our understanding. Sharing data and resources across countries will help to make significant breakthroughs in dark matter and dark energy research. These future research directions hold the promise of uncovering the true nature of the universe's most mysterious components. Each new discovery will bring us closer to a comprehensive understanding of the cosmos. The integrated Sachs-Wolf effect is a phenomenon observed in the cosmic microwave background. It occurs when CMB photons travel through time-varying gravitational potential wells. As the universe expands, the gravitational potential wells change, affecting the energy of the photons. This results in slight temperature fluctuations in the CMB. The effect provides evidence for the presence of dark energy. It indicates how the universe's expansion rate changes over time due to dark energy. The integrated Sachs-Wolf effect is more pronounced in areas where dark matter and dark energy interact strongly. It offers insights into the large-scale structure of the universe. By studying this effect, scientists can learn about the distribution of dark matter. It helps map out how dark matter and dark energy shape the cosmos. The effect is subtle and requires precise measurements to detect. Advanced telescopes and observatories are essential for observing these tiny fluctuations. The correlation between CMB temperature fluctuations and large-scale structures is key. This correlation is enhanced by the integrated Sachs-Wolf effect. Gravitational lensing can also amplify the integrated Sachs-Wolf effect. This amplification provides additional data points for studying dark energy and dark matter. Understanding this effect helps refine cosmological models. It bridges the gap between theory and observation, enhancing our understanding of the universe's evolution. Future missions aim to measure the integrated Sachs-Wolf effect with greater accuracy. Improved data will help test predictions about dark energy and the universe's expansion. The effect links the early universe to its current state. By studying it, scientists gain a continuous picture of cosmic history from the CMB to present-day structures. The effect also has implications for the geometry of the universe. It provides clues about the universe's curvature and overall shape. Theoretical models of dark energy are tested against observations of the integrated Sachs-Wolf effect. Consistency between theory and observation strengthens our confidence in these models. Machine learning and advanced algorithms aid in analyzing data related to the effect. These tools help identify patterns and enhance the precision of measurements. Ongoing research into the integrated Sachs-Wolf effect continues to reveal new aspects of the universe. Each discovery contributes to a deeper understanding of cosmic phenomena and the forces shaping our universe. Dark energy significantly influences the cosmic microwave background. It affects the universe's expansion rate, which in turn impacts the CMB's temperature fluctuations. As the universe expands faster due to dark energy, the gravitational potentials change. This change leads to the integrated Sachs-Wolf effect, causing slight variations in the CMB. The accelerated expansion stretches the wavelengths of the CMB photons. This stretching shifts the photons to longer wavelengths, altering the CMB spectrum. Dark energy's influence helps determine the universe's geometry. Observations of the CMB show a flat universe, consistent with the presence of dark energy. The early universe's conditions reflected in the CMB are shaped by dark energy. It affects the density fluctuations that lead to the formation of large-scale structures. Dark energy also impacts the polarization of the CMB. The patterns observed in the E-mode and B-mode polarizations provide clues about the nature of dark energy. By studying the CMB, scientists can infer the properties of dark energy. The data helps constrain models of how dark energy behaves over time. The gravitational lensing of the CMB by dark matter is influenced by dark energy. This lensing provides additional information about the distribution and effects of dark energy. Dark energy affects the overall energy budget of the universe. The CMB measurements show that dark energy dominates the current energy density of the universe. The impact of dark energy on the CMB helps refine cosmological parameters. Parameters like the Hubble constant are influenced by how dark energy affects the expansion rate. Future missions will provide more detailed measurements of the CMB. These missions aim to understand better how dark energy has influenced the universe's history. Improved data from these missions will help test theories of dark energy. The consistency of observations with theoretical predictions is crucial for validating these models. The influence of dark energy on the CMB is a key aspect of modern cosmology. It connects the early universe to its accelerated expansion observed today. Research into the CMB continues to uncover how dark energy shapes the cosmos. Each new finding enhances our understanding of this mysterious force. Understanding the influence of dark energy on the CMB helps answer fundamental questions about the universe's nature. It is essential for a comprehensive picture of cosmic evolution. Observational techniques for studying the cosmic microwave background are highly advanced and varied. Satellites like COBE, WMAP, and Planck have been pivotal in capturing detailed images of the CMB. These satellites are equipped with sensitive instruments to detect minute temperature fluctuations. They orbit above the Earth's atmosphere to avoid interference and gather precise data. Ground-based observatories also play a crucial role. Telescopes located in places like the Atacama Desert and the South Pole provide high-resolution measurements of the CMB. High-altitude balloons carry instruments above much of the atmosphere. Experiments like Boomerang and Spider use these balloons to collect clean data on the CMB's properties. Gravitational lensing is a key observational technique. By studying how the CMB light is bent by massive objects, scientists can map dark matter distribution. Polarization measurements are critical for understanding the CMB. Instruments like Polar Bear and the South Pole Telescope measure the polarization patterns to learn about the early universe. Fourier transform techniques are used to analyze the data. These techniques help separate the CMB signal from noise and other astrophysical sources. Direct detection methods focus on identifying interactions between dark matter and regular matter. Experiments like Xenon 1T use large volumes of liquid xenon to try to capture these rare events. Indirect detection methods look for signals from dark matter annihilation or decay. Telescopes such as the Fermi Gamma Ray Space Telescope search for excess gamma rays that could indicate dark matter. Astrophysical surveys map the large-scale structure of the universe. Projects like the Sloan Digital Sky Survey provide data on the distribution of galaxies and dark matter. Neutrino observatories detect high-energy neutrinos that could result from dark matter interactions. IceCube at the South Pole is one such observatory contributing to this research. Simulations and theoretical models guide observations. By comparing simulated data with actual observations, researchers refine their understanding of cosmic phenomena. Machine learning algorithms are increasingly used to analyze large data sets. These algorithms help identify patterns and correlations in the CMB data. Collaboration across disciplines enhances observational techniques. Astrophysicists, particle physicists, and cosmologists work together to develop new methods and technologies. Continued advancements in observational techniques are essential. They will help unravel the mysteries of dark matter and dark energy, deepening our understanding of the universe. One major discovery is the confirmation of the Big Bang theory through the CMB's uniformity. This finding provided strong evidence that the universe began from a hot, dense state. The detection of tiny temperature fluctuations in the CMB was another significant discovery. These anisotropies reveal the seeds of all cosmic structures, from galaxies to galaxy clusters. Measurements of the CMB have determined the universe's age with great precision. The data indicate that the universe is approximately 13.8 billion years old. The discovery of the acoustic peaks in the CMB spectrum has provided insights into the universe's composition. These peaks confirm the presence of dark matter and dark energy. Observations of the CMB have led to the discovery that the universe is flat. This geometric property aligns with predictions from the standard cosmological model. The detection of the integrated Sachs-Wolf effect provided evidence for dark energy. This effect shows how the universe's expansion rate changes due to dark energy. Polarization patterns in the CMB have been discovered, offering clues about the early universe. These patterns help scientists understand the ionization history and gravitational waves. The identification of the E-mode and B-mode polarizations has enhanced our knowledge of the CMB. E-modes relate to density fluctuations, while B-modes are linked to gravitational waves. Discovering the influence of dark matter on the CMB has been crucial. It helped confirm the existence of dark matter and its role in shaping cosmic structures. The Planck satellite's detailed map of the CMB provided the most precise data yet. This map has refined our understanding of cosmological parameters and supported the LCDM model. The discovery of gravitational lensing effects in the CMB has helped map dark matter. These effects distort the CMB patterns, offering insights into the distribution of dark matter. Finding evidence for cosmic inflation through the CMB's uniformity and fluctuations has been pivotal. Inflation explains the rapid expansion of the universe fractions of a second after the Big Bang. The discovery of the CMB's blackbody spectrum by COBE confirmed its thermal nature. This spectrum matches the predictions from the Big Bang model. Detecting the reionization signature in the CMB polarization has revealed details about the first stars and galaxies. This discovery provides insights into the universe's evolution after the Big Bang. Each major discovery from CMB studies has deepened our understanding of the universe. These findings continue to shape our knowledge of cosmology and the fundamental nature of the cosmos. Future prospects for studying the cosmic microwave background are incredibly exciting. New missions and advanced technology promise to reveal even more about the universe. The upcoming Euclid mission will map the dark universe with unprecedented precision. It aims to provide new insights into dark energy and the cosmic web structure. The James Webb Space Telescope will explore the earliest galaxies and stars. Its findings will help us understand how dark matter influenced their formation. Ground-based projects like the Simons Observatory will enhance our knowledge of the CMB's small-scale features. These observations will provide finer details of cosmic inflation and gravitational waves. High-altitude balloon missions will continue to offer clean data above the Earth's atmosphere. Experiments like Piper and Spider will focus on CMB polarization. Direct detection experiments will keep searching for dark matter particles. New technologies and methods aim to capture these elusive interactions. Particle accelerators like the Large Hadron Collider will probe for dark matter candidates. Discovering new particles could revolutionize our understanding of the cosmos. Astrophysical surveys will map galaxies with greater accuracy. Projects like the Vera C. Rubin Observatory will help track dark energy's impact on cosmic expansion. Advanced simulations will become even more detailed. By comparing these with observational data, researchers can refine their models of dark matter and dark energy. Collaborative efforts across disciplines will enhance research. Astrophysicists, particle physicists, and cosmologists will work together to solve these profound mysteries. Machine learning and artificial intelligence will play a larger role in data analysis. These tools will help uncover patterns and correlations in vast data sets. Future gravitational lensing studies will offer deeper insights. Enhanced maps will reveal more about dark matter's distribution and influence. Neutrino observatories will search for signals from dark matter interactions. Facilities like IceCube will continue to provide valuable data. Theoretical research will explore new models and hypotheses. Understanding dark energy and dark matter's true nature remains a top priority. International collaborations will be crucial for progress. Sharing resources and data globally will help advance our understanding of the universe. The future of CMB research holds great promise. Each new discovery will bring us closer to unlocking the secrets of the cosmos. The LCDM model is the standard model of cosmology. It stands for lambda cold dark matter, where lambda represents dark energy. This model explains the large-scale structure of the universe. It includes dark energy, dark matter, and ordinary matter. The LCDM model fits well with observations of the cosmic microwave background. It accurately describes the universe's expansion history. Dark energy, represented by lambda, drives the accelerated expansion of the universe. This component accounts for about 70% of the universe's energy density. Cold dark matter, the CDM part of the model, refers to dark matter that moves slowly compared to the speed of light. This type of dark matter helps form galaxies and large-scale structures. The model also includes ordinary matter, or baryonic matter. This is the matter that makes up stars, planets, and all visible structures. One of the strengths of the LCDM model is its simplicity. Despite its straightforward nature, it can explain a wide range of cosmological observations. The model predicts the temperature fluctuations seen in the CMB. These fluctuations match the patterns observed by missions like COBE, WMAP, and Planck. It also describes the distribution of galaxies in the universe. The large-scale structure surveys align with the predictions of the LCDM model. The LCDM model provides a framework for understanding cosmic inflation. It incorporates the rapid expansion of the universe shortly after the Big Bang. The model explains the observed flatness of the universe. Measurements of the CMB and other data confirm this flat geometry. The LCDM model also accounts for the integrated Sachs-Wolf effect. This effect is evidence of dark energy's influence on the CMB. Polarization data from the CMB further supports the LCDM model. The patterns observed match those predicted by the model. Despite its success, the LCDM model still faces challenges. The exact nature of dark energy and dark matter remains unknown. Continued research aims to refine and test the LCDM model. Each new observation and discovery helps improve our understanding of the universe. Alternatives to the LCDM model seek to explain the same observations through different mechanisms. One such alternative is the modified Newtonian dynamics, or MOND. MOND suggests modifying the laws of gravity at low accelerations. This theory aims to account for galaxy rotation curves without invoking dark matter. Another alternative is the FR gravity model. This approach modifies general relativity by altering the gravitational action to explain cosmic acceleration. The chameleon theory introduces a scalar field that changes properties based on the local environment. This allows dark energy to vary in strength depending on the matter density. Brane world models propose that our universe is a brane within a higher dimensional space. Gravity can leak into these extra dimensions, impacting cosmic expansion. K-essence theories involve dynamic scalar fields with non-standard kinetic energy terms. These fields evolve over time and can drive accelerated expansion. Quintessence models suggest a slowly evolving scalar field. Unlike the constant cosmological constant, quintessence varies, affecting the universe's expansion rate differently. Phantom energy theories propose an equation of state parameter less than -1. This leads to a more rapid acceleration, potentially ending in a Big Rip scenario. Interacting dark energy models explore the interaction between dark energy and dark matter. These interactions could influence the evolution of cosmic structures. Holographic dark energy theories are based on principles from quantum gravity. They propose that dark energy density is related to the universe's horizon. Cardassian expansion models modify the Friedmann equations. This approach alters how matter and energy density relate to the universe's expansion. Cosmic fluids with unusual properties are another alternative. These fluids can have negative pressure or other exotic characteristics that drive cosmic acceleration. Vacuum metamorphosis suggests a phase transition in vacuum energy. This transition could cause the observed acceleration without needing a constant dark energy component. Inhomogeneous cosmologies propose large-scale variations in matter distribution. These variations can affect measurements of cosmic acceleration and expansion. Exploring these alternatives helps test the robustness of the LCDM model. Each theory provides unique predictions, guiding future observations and experiments. Simulations and predictions play a crucial role in understanding dark matter and dark energy. These computational models help scientists visualize the universe's evolution. Cosmological simulations like the Millennium Simulation model, the large-scale structure of the universe. They include dark matter, dark energy, and ordinary matter to reproduce observed galaxy distributions. These simulations use the LCDM model as a framework. They track the formation and evolution of cosmic structures from the Big Bang to the present. By comparing simulations with observational data, researchers can test and refine their models. Discrepancies between the two provide clues about missing physics or incorrect assumptions. Simulations also help predict the effects of dark matter on galaxy formation. They show how dark matter clumps into halos, which then attract ordinary matter to form galaxies. Dark energy's influence on cosmic expansion is another focus of simulations. Models predict how dark energy accelerates the expansion and affects the growth of structures over time. Simulations can also explore alternative theories. By modifying the underlying physics, researchers can see how different models compare to the LCDM predictions. High-resolution simulations provide detailed predictions about small-scale structures. These include the distribution of dark matter within galaxies and the behavior of satellite galaxies. Gravitational lensing is another area where simulations are vital. They predict how light from distant objects is bent by dark matter, helping to map its distribution. Simulations aid in understanding the cosmic microwave background. They reproduce the temperature fluctuations and polarization patterns observed in the CMB. By including neutrinos, simulations can predict their impact on structure formation. This helps in understanding their role alongside dark matter and dark energy. Predictive models also explore the future of the universe. They can simulate scenarios like the Big Freeze, Big Rip, or Big Crunch based on different properties of dark energy. Machine learning techniques are increasingly used to enhance simulations. These methods can process large datasets and identify patterns that traditional techniques might miss. Simulations are continually refined with new data from telescopes and observatories. Each new piece of data helps improve the accuracy and reliability of the models. Ultimately, simulations and predictions are essential for testing cosmological theories. They provide a bridge between theoretical models and observable phenomena, guiding future research and discoveries. Comparing models with CMB data is crucial for testing cosmological theories. The CMB provides a snapshot of the universe at a young age, serving as a benchmark for models. The LCDM model fits well with CMB observations. It accurately predicts the temperature fluctuations and acoustic peaks seen in the CMB data. Alternative models are also tested against the CMB. By comparing their predictions with observed data, scientists can evaluate their validity and accuracy. The precision of CMB measurements allows for stringent tests of these models. Small discrepancies can reveal new physics or the need for adjustments in current theories. Polarization data from the CMB offers additional tests. Models must match not only the temperature fluctuations, but also the polarization patterns observed. Gravitational lensing effects seen in the CMB provide another comparison point. Accurate models need to reproduce these lensing patterns, reflecting the distribution of dark matter. The integrated Sachs-Wolf effect observed in the CMB is influenced by dark energy. Models that correctly predict this effect help confirm the presence and properties of dark energy. Comparing the large-scale structure of the universe with CMB data helps refine models. The distribution of galaxies and dark matter must align with the initial conditions indicated by the CMB. Neutrino masses and their impact on the CMB are also tested. Models incorporating different neutrino properties are compared with CMB observations to understand their role in cosmic evolution. High-resolution CMB data enables testing of small-scale fluctuations. Models must accurately predict these fine details to be considered robust. Simulations that incorporate CMB data provide insights into structure formation. By starting with CMB conditions, these simulations can track the development of galaxies and clusters. The consistency of CMB data with theoretical predictions strengthens the LCDM model. However, exploring deviations can lead to new discoveries and refinements in cosmological theories. Machine learning algorithms help analyze and compare models with CMB data. These techniques can identify subtle patterns and discrepancies, guiding further research. Future missions will provide even more precise CMB data. This will allow for more detailed comparisons and potentially reveal new aspects of the universe. The ongoing comparison of models with CMB data is essential for advancing our understanding of cosmology. It ensures that our theories accurately reflect the observable universe, guiding future discoveries and research directions. Implications for dark matter and dark energy from CMB studies are profound. They shape our understanding of these mysterious components of the universe. The CMB data confirms the existence of dark matter. Its gravitational effects are necessary to explain the observed temperature fluctuations. Dark matter's influence on the formation of galaxies and large-scale structures is also evident. Without it, the universe's structure would be drastically different. The amount of dark matter inferred from the CMB aligns with observations of galaxy rotation curves. This consistency supports the LCDM model. Dark energy's presence is implied by the accelerated expansion of the universe. The CMB data helps measure this acceleration, confirming dark energy's role. The integrated Sachs-Wolf effect observed in the CMB provides direct evidence for dark energy. This effect shows how dark energy influences gravitational potentials over time. Dark energy's impact on the universe's geometry is significant. The flatness of the universe, as indicated by CMB data, requires dark energy. Polarization measurements of the CMB offer clues about the early influence of dark energy. They help trace how dark energy affected the reionization era. The CMB data helps refine the equation of state for dark energy. Understanding this relationship is key to predicting the universe's ultimate fate. Comparing CMB data with large-scale structure surveys provides a comprehensive picture. This comparison helps understand how dark matter and dark energy interact. Simulations that match CMB observations offer insights into the nature of dark matter. They help predict its behavior and distribution in the universe. The consistency of CMB data with dark energy models strengthens our understanding. It confirms that dark energy is a major component driving cosmic acceleration. Future CMB studies will continue to refine these measurements. Improved data will help test new theories and models for dark matter and dark energy. The implications of these findings extend to fundamental physics. They challenge our understanding of gravity, particle physics, and the nature of the universe. As we continue to study the CMB, we gain deeper insights into dark matter and dark energy. Each discovery brings us closer to unraveling these cosmic mysteries. Satellites and space missions have been crucial for studying the cosmic microwave background. The Wilkinson Microwave Anisotropy Probe, or WMAP, provided detailed measurements of the CMB. WMAP launched in 2001 and operated until 2010. Its data helped refine estimates of the universe's age, composition, and development. The Planck satellite, launched by the European Space Agency in 2009, further improved CMB measurements. Planck provided the most detailed map of the CMB to date. Planck's instruments measured temperature fluctuations and polarization with high precision. This data has been essential for testing cosmological models. Both WMAP and Planck confirmed the LCDM model. Their findings support the presence of dark matter and dark energy in the universe. These missions also provided insights into cosmic inflation. The detailed CMB maps show patterns consistent with this rapid expansion theory. The Cosmic Background Explorer, or COBE, was an earlier mission that first detected CMB anisotropies. Launched in 1989, COBE's findings were groundbreaking. COBE's detection of tiny temperature variations in the CMB earned its team the Nobel Prize. These variations are the seeds of all cosmic structure. High-altitude balloon missions like Boomerang and Maxima also contributed valuable data. They complemented satellite observations by measuring the CMB from the stratosphere. The upcoming Euclid mission will map the geometry of the dark universe. By observing billions of galaxies, it will provide new insights into dark energy and dark matter. The James Webb Space Telescope will study the formation of the first galaxies and stars. Its observations will help understand how dark matter influenced these early structures. The Simons Observatory, set to begin operation soon, will focus on CMB polarization. It aims to detect gravitational waves from the early universe. Future missions will continue to improve CMB measurements. Each new satellite or observatory brings the potential for significant discoveries. These space missions are vital for advancing our understanding of cosmology. They provide the precise data needed to test theories and refine models. As technology advances, new missions will offer even more detailed views of the CMB. These observations will help answer fundamental questions about the universe's origins and evolution. Ground-based telescopes play a crucial role in studying the cosmic microwave background. These observatories provide high-resolution measurements of the CMB's small-scale features. The Atacama Cosmology Telescope is one such facility. Located in Chile's Atacama Desert, it benefits from dry, stable atmospheric conditions. Another significant observatory is the South Pole Telescope. Positioned at the Earth's southernmost point, it offers a clear, unobstructed view of the sky. These ground-based telescopes complement satellite missions. They provide additional data and can focus on specific regions of the sky with greater detail. High-altitude balloon experiments like Boomerang have also contributed. By flying above much of the atmosphere, they reduce interference and improve data quality. The Simons Observatory, currently under construction, will be a major new facility. It aims to make precise measurements of CMB polarization to detect signals from the early universe. Ground-based telescopes use various techniques to measure the CMB. These include radiometers and bolometers, which detect microwave radiation with high sensitivity. Polarization measurements are a key focus. Instruments like Polar Bear and Bicep 2 are designed to detect the faint polarization patterns in the CMB. These measurements help scientists study gravitational waves from the early universe. Detecting these waves would provide evidence for cosmic inflation. Gravitational lensing studies are also conducted with ground-based telescopes. They map the distribution of dark matter by observing how it bends light from distant objects. Observations from these telescopes help refine cosmological parameters. They provide data on the Hubble constant, the universe's curvature, and the distribution of dark matter and dark energy. The collaboration between ground-based and space-based observatories enhances our understanding. Each type of observatory offers unique strengths and perspectives. Ground-based telescopes are continuously upgraded with new technology. These improvements increase their sensitivity and resolution, allowing for more detailed studies of the CMB. Future projects like the Simons Observatory will push the boundaries of CMB research. They aim to provide even more precise data to test and refine cosmological models. These observatories are essential for advancing our knowledge of the universe. They help us understand the fundamental nature of cosmic phenomena and the evolution of the cosmos. Data analysis techniques are crucial for interpreting observations of the cosmic microwave background. These techniques help extract meaningful information from vast datasets. One key method is the Fourier transform. It converts data from the time or space domain into the frequency domain, revealing patterns and structures in the CMB. Another technique is map making, which involves constructing detailed maps of the sky from raw data. These maps show temperature fluctuations and polarization in the CMB. Component separation is used to isolate the CMB signal from foreground emissions. This involves distinguishing between the CMB and other sources like galactic dust and synchrotron radiation. Statistical methods play a significant role in CMB analysis. These methods help quantify the anisotropies and extract cosmological parameters from the data. Power spectrum analysis is a common approach. It examines the distribution of temperature fluctuations across different scales, providing insights into the universe's composition and structure. Markov chain Monte Carlo algorithms are used to explore parameter space. These algorithms help estimate the values of cosmological parameters by sampling from their probability distributions. Principal component analysis reduces the dimensionality of data. It identifies the most important variables and patterns, simplifying the analysis of complex datasets. Machine learning techniques are increasingly applied to CMB data. These techniques can identify patterns and correlations that might be missed by traditional methods. Bayesian inference is used to update the probability of a hypothesis as more data becomes available. This approach helps refine models and improve parameter estimates. Cross-correlation studies compare CMB data with other astronomical observations. This helps verify findings and provides a more comprehensive understanding of cosmic phenomena. Simulations play a crucial role in data analysis. They create synthetic datasets based on theoretical models, allowing researchers to test their methods and interpret real data. Blind analysis techniques are employed to prevent bias. Analysts are kept unaware of certain aspects of the data until the analysis is complete, ensuring objective results. Wavelet transforms are used to analyze localized variations in the data. They provide a multi-resolution view, capturing both large-scale structures and small-scale details. Ongoing advancements in data analysis techniques are essential for cosmology. They enable researchers to extract the maximum amount of information from observations, deepening our understanding of the universe. Recent advancements in cosmology have significantly enhanced our understanding of the universe. Improved technology and innovative methods have led to more precise measurements of the cosmic microwave background. The Planck satellite provided the most detailed map of the CMB, offering high-resolution data. This map has refined our understanding of the universe's age, composition, and structure. The detection of B-mode polarization by experiments like BICEP-2 was a breakthrough. This polarization pattern is linked to gravitational waves from cosmic inflation. Advances in ground-based telescopes, such as the South Pole Telescope, have improved our ability to study the CMB's small-scale features. These telescopes provide complementary data to space missions. High-altitude balloon experiments like SPIDER have achieved cleaner data by reducing atmospheric interference. These missions contribute valuable information on CMB polarization. Machine learning algorithms are now widely used in data analysis. These algorithms can process large data sets efficiently, identifying patterns and extracting critical information. The integration of artificial intelligence in cosmology has opened new avenues for research. AI helps automate data processing and improves the accuracy of cosmological models. Enhanced simulations have become more detailed and accurate. By incorporating more physical processes, these simulations better match observational data. Interdisciplinary collaborations have strengthened research efforts. Astrophysicists, particle physicists, and computer scientists work together to tackle complex cosmological questions. New particle physics experiments aim to detect dark matter directly. These experiments use advanced detectors and methods to search for interactions between dark matter and ordinary matter. Gravitational lensing studies have become more precise, mapping dark matter with greater accuracy. This helps understand the distribution and properties of dark matter in the universe. The development of next-generation telescopes, like the James Webb Space Telescope, promises to revolutionize our understanding of the early universe. These telescopes will observe the formation of the first galaxies and stars. Polarization measurements continue to improve, providing deeper insights into the early universe. Enhanced instruments are detecting fainter signals, offering more detailed data. The Euclid mission, set to launch soon, will map the dark universe with unprecedented precision. It aims to study dark energy and its effects on the cosmic web's structure. These recent advancements are driving cosmology forward, continually refining our models and expanding our knowledge of the universe's fundamental properties. Each new discovery builds on previous work, bringing us closer to solving the mysteries of dark matter and dark energy. Future technological developments in cosmology promise to revolutionize our understanding of the universe. New instruments and methods will enhance the precision and scope of our observations. Next-generation telescopes like the James Webb Space Telescope will provide unprecedented views of the early universe. They will observe the formation of the first stars and galaxies in great detail. The upcoming Euclid mission aims to map the geometry of the dark universe. By observing billions of galaxies, it will shed light on dark energy and its effects on cosmic expansion. Ground-based telescopes will continue to advance. Projects like the Vera C. Rubin Observatory will conduct deep sky surveys, improving our knowledge of dark matter and dark energy. High-altitude balloon missions will offer clearer data above much of the Earth's atmosphere. Experiments like Piper and Spider will focus on measuring CMB polarization with high precision. Advances in detector technology will increase sensitivity to faint cosmic signals. New materials and designs will help capture interactions that were previously undetectable. Quantum computing holds promise for processing vast amounts of cosmological data. These powerful computers can handle complex simulations and analyses at unprecedented speeds. Artificial intelligence and machine learning will play an even greater role. These technologies will help automate data analysis, uncover patterns, and refine cosmological models. Interdisciplinary research will drive innovation. Collaborations between physicists, engineers, and computer scientists will lead to the development of cutting-edge tools and techniques. Enhanced simulations will incorporate more physical processes and higher resolution. These simulations will better match observational data, providing deeper insights into the universe's evolution. Gravitational wave detectors will continue to improve. These instruments will help study cosmic events and test theories of dark matter and dark energy. Advanced particle physics experiments will search for dark matter candidates with greater precision. New detectors and methods will increase the chances of direct detection. Cosmic neutrino observatories will detect high-energy neutrinos from dark matter interactions. These observations will provide indirect evidence of dark matter's presence. Global collaborations will enhance research capabilities. Sharing data and resources across countries will lead to more comprehensive studies and significant breakthroughs. As technology advances, each new development will bring us closer to understanding the fundamental nature of the universe. These future innovations hold the key to unraveling the mysteries of dark matter and dark energy. Mapping the early universe involves capturing the distribution of matter and energy shortly after the Big Bang. The cosmic microwave background serves as a snapshot of this period. The CMB provides a detailed picture of the universe when it was just 380,000 years old. Analyzing the CMB helps us understand the initial conditions that led to the formation of galaxies and large-scale structures. High-resolution maps of the CMB reveal tiny temperature fluctuations. These fluctuations represent density variations in the early universe. Satellite missions like COBE, WMAP, and Planck have been instrumental in mapping the CMB. Their observations provide precise data on the temperature and polarization of the CMB. Ground-based telescopes complement these satellite missions. They offer additional high-resolution observations of specific regions of the sky. Mapping the early universe also involves studying the distribution of galaxies. Large-scale surveys like the Sloan Digital Sky Survey map the positions and properties of millions of galaxies. These surveys help trace the cosmic web, the large-scale structure of the universe. The distribution of galaxies and dark matter forms a web-like pattern, influenced by the initial conditions captured in the CMB. Gravitational lensing studies provide insights into the distribution of dark matter. By observing how light is bent by massive objects, scientists can map the invisible dark matter. Neutrino observatories help map the early universe by detecting high-energy neutrinos. These particles carry information about processes that occurred shortly after the Big Bang. Advanced simulations play a crucial role in mapping the early universe. By modeling the evolution of the universe from the Big Bang to the present, scientists can compare these simulations with observational data. Machine learning algorithms enhance the analysis of large datasets. These techniques help identify patterns and correlations in the distribution of matter and energy. Future missions aim to improve our maps of the early universe. The Euclid mission and the James Webb Space Telescope will provide new data on the distribution of galaxies and dark matter. The study of cosmic inflation is also part of mapping the early universe. Inflationary models predict specific patterns in the CMB, which can be tested with precise measurements. Polarization measurements of the CMB provide additional information about the early universe. They help trace the reionization era and the influence of gravitational waves. Each new map of the early universe brings us closer to understanding its origins and evolution. These maps are essential tools for testing cosmological models and theories about the fundamental nature of the cosmos. Insights into dark matter have come primarily from its gravitational effects. Observations of galaxy rotation curves first suggested its presence, as stars in the outer regions of galaxies rotate faster than visible matter alone can explain. Galaxy clusters provide additional evidence. The gravitational pull needed to keep these clusters together exceeds what can be accounted for by visible matter alone, implying the existence of dark matter. Gravitational lensing studies offer a way to map dark matter. By observing how light from distant objects is bent by massive galaxy clusters, scientists can infer the distribution of dark matter. The cosmic microwave background also reveals the influence of dark matter. Tiny fluctuations in the CMB's temperature are shaped by the gravitational effects of dark matter in the early universe. Dark matter plays a crucial role in the formation of large-scale structures. Its gravitational pull helps clump ordinary matter together, leading to the formation of galaxies and clusters. Simulations of the universe's evolution that include dark matter match observed structures. These simulations show how dark matter acts as a scaffold for ordinary matter to form stars and galaxies. Direct detection experiments aim to observe dark matter particles interacting with normal matter. These experiments, like Xenon 1T, are conducted deep underground to shield them from cosmic rays. Indirect detection methods look for the products of dark matter annihilation or decay. Observatories like the Fermi Gamma Ray Space Telescope search for excess gamma rays that could indicate dark matter. High-energy particle colliders, such as the Large Hadron Collider, attempt to produce dark matter particles. Discovering these particles would provide direct evidence of dark matter. Neutrino observatories may also detect signals from dark matter. High-energy neutrinos produced by dark matter interactions could provide additional clues. Studies of the large-scale structure of the universe further support the presence of dark matter. The distribution and movement of galaxies align with predictions involving dark matter. Dark matter influences the cosmic web, the vast network of filaments and voids in the universe. Its gravitational effects help shape this large-scale structure. The study of cosmic microwave background anisotropies provides detailed insights into dark matter. The observed patterns in the CMB fit well with models that include dark matter. Polarization measurements of the CMB add another layer of understanding. These measurements help trace how dark matter influenced the early universe's evolution. Each new observation and experiment enhances our understanding of dark matter. These insights are crucial for developing a complete picture of the universe's composition and evolution. Insights into dark energy primarily come from observing the universe's accelerated expansion. Distant supernovae studies first indicated that the expansion rate is increasing. The cosmic microwave background provides additional evidence. Patterns in the CMB, especially the integrated Sachs-Wolf effect, show how dark energy influences the universe's growth. The large-scale structure of the universe also hints at dark energy. Galaxy surveys reveal a distribution pattern consistent with the presence of dark energy. Gravitational lensing studies help map the distribution of dark energy. By observing the bending of light, scientists can infer the influence of dark energy on cosmic structures. Baryon acoustic oscillations offer another method to study dark energy. These regular spacing of galaxies act as a cosmic ruler, helping to measure the universe's expansion history. The equation of state parameter for dark energy is a key focus. Understanding whether dark energy is constant or varies over time impacts models of cosmic evolution. Polarization measurements of the CMB provide additional insights. They help trace how dark energy has influenced the universe since the reionization era. Dark energy affects the growth of cosmic structures. It counteracts gravity, slowing down the formation of galaxy clusters. Numerical simulations incorporating dark energy match observed cosmic structures. These simulations help refine our understanding of dark energy's role in the universe. High-precision measurements of the Hubble constant help constrain dark energy models. Discrepancies in these measurements can indicate new physics or the need to adjust current models. Future missions like Euclid aim to map dark energy more precisely. By studying billions of galaxies, Euclid will provide deeper insights into dark energy's effects on cosmic expansion. The study of dark energy also involves testing general relativity on cosmic scales. Any deviations could point to new physics or modifications needed in our understanding of gravity. Interdisciplinary research, combining astrophysics, particle physics, and cosmology, is crucial. This collaborative approach helps develop comprehensive models of dark energy. Observations of high-energy cosmic phenomena, such as gamma-ray bursts, also contribute. These events provide unique data points for understanding dark energy. Each new discovery about dark energy deepens our understanding of the universe's fate. These insights are essential for building a complete picture of cosmic evolution and the fundamental forces at play. Unexpected anomalies in the cosmic microwave background have intrigued scientists. These anomalies challenge our current understanding of the universe. One such anomaly is the cold spot. This region in the CMB is significantly cooler than the surrounding areas, which is difficult to explain with standard models. Another anomaly is the alignment of the CMB's large-scale features. Known as the axis of evil, this alignment appears inconsistent with the expected random distribution. The lack of power at large angular scales in the CMB is also puzzling. This suggests less fluctuation on the largest scales than predicted by the standard model. Anomalies in the polarization patterns of the CMB have been observed. These deviations might indicate new physics or unknown processes in the early universe. The dipole anisotropy is another unexpected feature. It shows a significant difference in temperature along one direction, raising questions about our motion relative to the CMB. Some anomalies are linked to potential foreground contamination. Galactic dust and other sources might influence the observed CMB, complicating the interpretation. The hemispherical asymmetry in the CMB is also surprising. One half of the sky shows more fluctuation than the other, challenging the notion of isotropy. Unexpected patterns in the gravitational lensing of the CMB have been detected. These patterns might point to unknown structures or properties of dark matter. Anomalies in the spectral index of primordial fluctuations have been noted. These variations suggest deviations from the simple inflationary models. Large voids, such as the Eridanus supervoid, correlate with CMB anomalies. These voids might contribute to the cold spot or other features in the CMB. The study of CMB anomalies involves testing alternative models. These models explore new physics, such as modified gravity or interactions between dark matter and dark energy. Cosmic strings and other topological defects have been proposed to explain certain anomalies. These hypothetical structures could leave imprints on the CMB. Future missions aim to provide more precise measurements of these anomalies. Improved data will help clarify whether these features are real or artifacts. Understanding these anomalies is crucial for refining our cosmological models. They offer potential windows into new physics and deeper insights into the universe's origins. Each unexpected finding pushes the boundaries of our knowledge. Investigating these anomalies helps us explore the limits of current theories and the possibilities beyond. Controversies and debates are a natural part of advancing our understanding of the universe. One major debate concerns the exact value of the Hubble constant, which measures the universe's expansion rate. Different methods of measuring the Hubble constant yield different results. This discrepancy, known as the Hubble tension, has sparked intense discussions in the scientific community. Another controversy involves the nature of dark matter. While most evidence supports its existence, the exact composition of dark matter remains unknown, leading to various competing theories. The role of dark energy is also a topic of debate. Some scientists propose that what we perceive as dark energy might be due to modifications in our understanding of gravity. The interpretation of CMB anomalies sparks significant debate. Some researchers argue these anomalies point to new physics, while others believe they result from observational or data processing errors. The potential existence of primordial gravitational waves has been controversial. Initial claims of their detection were later attributed to galactic dust, raising questions about the methods used. The concept of cosmic inflation itself is debated. While inflation explains many observed features of the universe, alternative theories continue to be explored. The axis of evil anomaly in the CMB challenges the assumption of a perfectly isotropic universe. Whether this is a real feature or a result of data artifacts remains contested. Gravitational lensing studies sometimes show discrepancies with predictions. These differences lead to debates about the distribution of dark matter and the assumptions made in models. The interpretation of large-scale structure surveys can be contentious. Different methods of analyzing data can lead to varying conclusions about the universe's composition and behavior. The possibility of sterile neutrinos as a component of dark matter generates debate. While they could solve certain anomalies, they have yet to be definitively detected. Modifications to general relativity are proposed to explain dark energy. These modifications face both theoretical and observational challenges, fueling ongoing debates. The exact mechanisms behind cosmic reionization are not fully understood. Different models propose various sources for the first ionizing photons, leading to discussions on early galaxy formation. The future of direct dark matter detection experiments is hotly debated. While some believe we are on the verge of a breakthrough, others argue that our current methods may not be sufficient. Controversies and debates drive the field of cosmology forward. By challenging assumptions and exploring alternative theories, scientists refine their models and deepen our understanding of the universe. Measurement accuracy is crucial in cosmology to ensure reliable data. Advanced technology and methods are employed to achieve high precision. Satellites like Planck have provided incredibly accurate measurements of the CMB. Their instruments are designed to detect minute temperature fluctuations with great sensitivity. Ground-based telescopes contribute by offering high-resolution data. These observatories complement satellite data, providing detailed views of specific sky regions. Calibration of instruments is vital for accuracy. Regular calibration checks help maintain the precision of measurements over time. Data processing techniques are continually refined. Sophisticated algorithms help minimize errors and extract meaningful information from raw data. Cross-validation with different instruments enhances accuracy. Comparing data from various sources ensures consistency and reliability. Foreground contamination is a significant challenge. Separating the CMB signal from galactic and extragalactic sources requires careful analysis. Polarization measurements demand extreme precision. Instruments like Polar Bear and Bicep 2 are designed to detect faint polarization patterns in the CMB. Gravitational lensing studies rely on precise measurements of light bending. Accurate mapping of lensing effects helps understand dark matter distribution. High-altitude balloon missions reduce atmospheric interference. By flying above most of the atmosphere, these missions achieve cleaner data. Interdisciplinary collaboration improves measurement techniques. Physicists, engineers, and computer scientists work together to develop better tools and methods. Machine learning enhances data analysis accuracy. These algorithms can identify patterns and correct for potential errors in large data sets. Neutrino observatories require precise detection methods. High-energy neutrinos are challenging to observe, and accuracy is essential for reliable data. Future missions aim to improve measurement accuracy further. Advancements in technology and methodology will lead to even more precise cosmological data. Accurate measurements are foundational for testing and refining cosmological models. Each improvement in accuracy brings us closer to understanding the universe's true nature. Interpretational difficulties arise when analyzing complex cosmological data. The vast amount of information and the subtle signals make it challenging to draw clear conclusions. One major difficulty is distinguishing between different cosmological models. Many models can fit the same data, making it hard to determine which one is correct. Another challenge is dealing with foreground contamination. Signals from the Milky Way and other sources can interfere with the cosmic microwave background data. Cosmic variance also complicates interpretation. This statistical uncertainty arises because we can only observe one universe and must infer properties from limited data. Small-scale anomalies in the CMB are hard to interpret. These anomalies might suggest new physics, or could result from data processing errors or foreground interference. Gravitational lensing studies present their own challenges. Accurately mapping dark matter distributions requires careful interpretation of the bending of light. The polarization of the CMB adds another layer of complexity. Differentiating between E-mode and B-mode polarization involves precise measurements and sophisticated analysis. Interpreting signals from direct dark matter detection experiments is difficult. Background noise and rare events make it hard to confirm dark matter interactions. Neutrino data can be challenging to interpret due to their weak interactions. Distinguishing between different neutrino sources and understanding their implications requires careful analysis. The discrepancies in Hubble constant measurements highlight interpretational difficulties. Different methods yield different values, leading to debates about the universe's expansion rate. Interpreting high-energy cosmic events involves many uncertainties. These events provide valuable data but are often rare and complex, complicating their analysis. Theoretical models sometimes predict similar outcomes, making it hard to differentiate between them. This overlap requires careful scrutiny of predictions and observations. Understanding the role of dark energy involves significant interpretational challenges. Its effects are subtle and require precise measurements to discern accurately. Simulations help interpret cosmological data but come with their own difficulties. Ensuring that simulations accurately reflect reality involves many assumptions and approximations. Continuous advancements in technology and methodology are essential to overcome these interpretational difficulties. Each step forward helps clarify our understanding of the universe and its underlying principles. Limitations of current models highlight gaps in our understanding of the universe. Despite their successes, these models cannot explain every observation. One limitation is the unknown nature of dark matter. While it fits the gravitational effects we observe, its exact composition remains a mystery. Dark energy is another significant unknown. Our models account for its effects on cosmic expansion, but we don't understand its fundamental properties. The LCDM model, though successful, cannot explain all cosmological anomalies. Features like the cold spot and the axis of evil challenge this model's completeness. Inflation theory, while explaining the early universe's rapid expansion, lacks a clear mechanism. The exact process driving inflation is still speculative. Current models also struggle with a Hubble tension. Different methods of measuring the universe's expansion rate yield conflicting results, suggesting new physics might be needed. The nature of dark matter interactions is poorly understood. Direct detection experiments have yet to yield definitive results, indicating our models might need refinement. Models predicting dark energy's behavior vary widely. Whether it is a cosmological constant or a dynamic field remains an open question. The distribution of matter in the universe presents challenges. Simulations and observations sometimes show discrepancies that our models can't fully explain. Cosmic reionization details are still unclear. The sources and timeline of reionization need better constraints from both observations and models. Neutrino masses and their impact on cosmology remain uncertain. Models must account for these light particles, but their exact properties and effects are not fully known. The exact role of cosmic magnetic fields is another gap. Their influence on galaxy formation and evolution is not well understood within current models. Primordial gravitational waves are predicted but not yet detected. Their absence challenges inflation models that predict their existence. Alternative theories of gravity offer potential solutions, but face their own issues. These models often struggle to match the success of general relativity across all scales. Understanding the initial conditions of the universe is still a challenge. Models must make assumptions that might not hold true in reality. Continued observations and advancements in technology are essential. These will help refine current models and potentially develop new ones to address these limitations. Technical challenges in cosmology often stem from the complexity of the instruments and methods required. Building and maintaining highly sensitive detectors is a significant hurdle. These detectors must be shielded from cosmic rays and other sources of noise. This often requires placing them deep underground or in remote locations. Space missions face additional challenges, such as the harsh conditions of space. Instruments must be robust and reliable to function correctly over long periods. Achieving the necessary precision in measurements is difficult. Small errors can lead to significant discrepancies in data interpretation. Calibration of instruments is essential but challenging. Regular calibration ensures accuracy but can be technically demanding and resource-intensive. Data processing requires sophisticated algorithms. These algorithms must handle vast amounts of data and extract meaningful information without introducing biases. Separating the cosmic microwave background signal from foreground noise is complex. This process involves distinguishing the CMB from galactic dust and other sources. Polarization measurements need extreme precision. Detecting faint polarization patterns requires highly sensitive instruments and careful analysis. Gravitational lensing studies depend on accurate mapping of light distortion. This requires precise observations and detailed models to interpret the data correctly. High-altitude balloon missions must contend with atmospheric conditions. These conditions can affect data quality and the stability of the instruments. Developing new materials for detectors is another technical challenge. These materials must be highly sensitive to faint cosmic signals, yet durable enough to last. Interdisciplinary collaboration is necessary but challenging. Coordinating efforts between physicists, engineers, and computer scientists requires effective communication and integration of expertise. Handling the sheer volume of data from modern telescopes is a logistical challenge. Efficient storage, processing, and analysis methods are essential to manage this data. Machine learning and artificial intelligence tools are helpful, but require significant development. These tools must be trained on vast datasets to improve their accuracy and reliability. Future advancements depend on overcoming these technical challenges. Each solution will bring us closer to understanding the universe and its fundamental components. Overcoming these challenges requires innovation and collaboration. New technologies are being developed to enhance the sensitivity and precision of detectors. Shielding detectors from noise involves placing them in remote or underground locations. This helps minimize interference from cosmic rays and other sources. Space missions need robust designs to withstand harsh conditions. Engineers are developing more durable instruments that can operate reliably over long periods. Achieving precise measurements involves regular calibration. Advanced calibration techniques ensure that instruments maintain their accuracy over time. Sophisticated data processing algorithms are essential. These algorithms can handle vast amounts of data and extract meaningful information while minimizing biases. To separate the CMB signal from foreground noise, scientists use advanced modeling techniques. These models help distinguish the CMB from other sources like galactic dust. Polarization measurements benefit from highly sensitive instruments. Improved detector technology allows for more accurate detection of faint polarization patterns. Gravitational lensing studies require precise mapping. Enhanced observational techniques and detailed models help interpret the data correctly. High-altitude balloon missions are improving. Better materials and design innovations ensure stable instruments and high-quality data in variable atmospheric conditions. Developing new materials for detectors is ongoing. Research into highly sensitive yet durable materials continues to advance. Interdisciplinary collaboration is being strengthened. Improved communication and integration of expertise from various fields enhance the development of new technologies and methods. Managing the volume of data from modern telescopes involves efficient storage and processing solutions. Advances in data management technology help handle these large data sets. Machine learning and AI tools are being refined. Training these tools on vast data sets improves their accuracy and reliability, aiding in data analysis. Future advancements depend on continued innovation. Solving these technical challenges will lead to more precise observations and a deeper understanding of the universe. Collaboration across disciplines and countries is crucial. Sharing resources and expertise accelerates progress and helps overcome the technical challenges in cosmology. Upcoming missions and projects promise to advance our understanding of the universe. The Euclid mission, set to launch soon, aims to map the dark universe with unprecedented precision. The James Webb Space Telescope will explore the formation of the first galaxies and stars. Its advanced instruments will provide new insights into the early universe. The Simons Observatory is a major ground-based project. It will focus on detailed measurements of the cosmic microwave background and its polarization. The Vera C. Rubin Observatory will conduct deep sky surveys. These surveys will enhance our knowledge of dark matter and dark energy by mapping millions of galaxies. The Piper balloon experiment will measure CMB polarization. Flying at high altitudes, it will reduce atmospheric interference and capture cleaner data. Advanced particle detectors like those in the Xenon T experiment aim to directly detect dark matter. These detectors are more sensitive and capable of capturing rare interactions. The Dark Energy Spectroscopic Instrument will map the universe's expansion. By observing millions of galaxies, it will provide new data on dark energy. The Laser Interferometer Space Antenna, or LISA, will detect gravitational waves from space. It will help study cosmic events and test theories of dark matter and dark energy. The Square Kilometre Array is an ambitious radio telescope project. It will observe the universe with unparalleled sensitivity, contributing to our understanding of cosmic evolution. The CMB-S4 project will be the next generation of ground-based CMB experiments. It aims to achieve extremely high precision in measuring the CMB's temperature and polarization. Future upgrades to the Large Hadron Collider will enhance its capabilities. These upgrades will enable more detailed searches for dark matter particles. The IceCube Neutrino Observatory is being expanded. New detectors will increase its sensitivity to high-energy neutrinos from cosmic sources. The Lynx X-ray Observatory will study high-energy phenomena in the universe. It will provide detailed images of black holes, galaxy clusters, and other cosmic structures. The Advanced Telescope for High-Energy Astrophysics, or Athena, will observe the universe in X-rays. It aims to uncover the physical processes driving cosmic evolution. These upcoming missions and projects represent the forefront of cosmological research. Each will contribute unique data and insights, pushing the boundaries of our understanding. Innovative methods and techniques are driving advancements in cosmology. Machine learning algorithms are increasingly used to analyze vast amounts of data efficiently. AI tools help identify patterns and correlations that might be missed by traditional methods. These tools improve the accuracy and speed of data processing. Quantum computing holds promise for complex simulations. These powerful computers can handle large datasets and intricate models with unprecedented speed. High-resolution simulations are becoming more detailed. They incorporate more physical processes, providing better matches to observational data. Adaptive optics technology enhances ground-based telescopes. By correcting for atmospheric distortions in real time, this technology sharpens images and improves data quality. Interferometry techniques combine data from multiple telescopes. This method increases resolution and sensitivity, allowing for more detailed observations of cosmic phenomena. Cryogenic detectors operate at extremely low temperatures. These detectors reduce thermal noise, increasing the sensitivity to faint cosmic signals. Advanced calibration techniques ensure the precision of measurements. Regular calibration checks and novel methods help maintain the accuracy of observational data. Polarimetry is being refined to study the polarization of light. This technique provides insights into the magnetic fields and scattering processes in cosmic structures. Gravitational lensing analyses are becoming more sophisticated. Improved models and methods help map dark matter distribution with greater accuracy. New materials are being developed for detectors. These materials enhance sensitivity and durability, crucial for capturing weak signals from distant sources. Spectroscopy techniques are advancing to study the composition of cosmic objects. High-resolution spectra provide detailed information about the chemical and physical properties of stars and galaxies. Balloon-borne experiments are benefiting from innovative designs. Enhanced stability and data collection methods improve the quality of measurements. Collaborative platforms are facilitating interdisciplinary research. Scientists from various fields work together, sharing data and expertise to solve complex cosmological problems. These innovative methods and techniques are essential for overcoming current limitations. They pave the way for new discoveries and a deeper understanding of the universe. Interdisciplinary approaches are crucial for advancing our understanding of cosmology. Collaboration between astrophysicists, particle physicists, and engineers leads to innovative solutions. These diverse fields bring unique perspectives and expertise. Combining their strengths helps tackle complex problems in new and effective ways. Data scientists play a vital role in analyzing vast data sets. Their expertise in machine learning and AI enhances the accuracy and efficiency of data processing. Chemists and material scientists contribute by developing new detector materials. These materials increase sensitivity and durability, crucial for long-term observations. Collaboration with computer scientists improves simulation capabilities. Advanced algorithms and high-performance computing enable more detailed and accurate models. Interdisciplinary research fosters creative problem-solving. It encourages the integration of different techniques and technologies, leading to breakthroughs. Biologists and medical researchers also contribute. Techniques from medical imaging are adapted for use in astronomical observations, improving image resolution. Environmental scientists help mitigate observational interference. Understanding atmospheric conditions aids in designing better ground-based telescopes and balloon experiments. Economists and statisticians provide valuable insights into data analysis. Their methods help quantify uncertainties and refine models of cosmic phenomena. Policymakers and social scientists ensure that research aligns with public interests. They help secure funding and support for large-scale scientific projects. Educational specialists enhance public understanding of cosmology. Effective communication strategies engage and inform the public about scientific discoveries. Historians of science provide context and perspective. They trace the development of cosmological theories, helping current researchers build on past knowledge. Philosophers explore the implications of cosmological findings. They address questions about the nature of the universe and our place within it. Interdisciplinary conferences and workshops foster collaboration. These events bring together experts from various fields to share knowledge and ideas. By embracing interdisciplinary approaches, cosmology advances more rapidly. This collaborative spirit drives innovation and deepens our understanding of the universe. Potential breakthroughs in cosmology could revolutionize our understanding of the universe. One such breakthrough would be the direct detection of dark matter particles, confirming their existence and properties. A deeper understanding of dark energy could also be transformative. Discovering its nature and origin would answer fundamental questions about the universe's accelerated expansion. Detecting primordial gravitational waves would provide strong evidence for cosmic inflation. These waves would offer insights into the universe's earliest moments. New particles discovered at high-energy colliders could change our understanding of fundamental physics. These discoveries might explain dark matter or reveal new forces. Advancements in neutrino research could shed light on their role in the universe. Understanding neutrino masses and properties would impact models of cosmic evolution. Improved measurements of the Hubble constant could resolve the Hubble tension. This would unify different methods of measuring the universe's expansion rate. Observations from the James Webb Space Telescope could reveal the formation of the first galaxies and stars. These insights would enhance our understanding of early cosmic history. The detection of cosmic strings or other topological defects would support new physics theories. These structures would offer evidence for phenomena beyond the standard model. Breakthroughs in AI and machine learning could revolutionize data analysis. Enhanced algorithms would identify patterns and correlations, accelerating discoveries. Discovering the true nature of dark energy could lead to new physics. This could involve modifications to general relativity or entirely new theories. High-precision maps of the cosmic microwave background could reveal subtle anomalies. These anomalies might suggest new physics or refine existing models. Innovations in detector technology could improve sensitivity to faint cosmic signals. This would enhance the search for dark matter and other elusive phenomena. Interdisciplinary research could lead to unexpected breakthroughs. Combining expertise from various fields often results in innovative solutions and new insights. International collaborations could accelerate progress. Sharing data and resources globally ensures comprehensive studies and significant advancements. Each potential breakthrough brings us closer to understanding the universe's mysteries. Continued research and innovation hold the promise of unlocking new knowledge and transforming cosmology. We've explored the fascinating realms of dark matter and dark energy, delving into their influence on the cosmic microwave background. We began by understanding the discovery and significance of the CMB, which provides a snapshot of the universe shortly after the Big Bang. We examined the properties of the CMB and the sophisticated methods used to measure it. Ground-based telescopes, high-altitude balloons, and advanced satellite missions all contribute to our detailed understanding of this cosmic relic. We discussed how dark matter, an elusive substance, leaves its imprint on the CMB. Its gravitational effects help shape the universe's large-scale structures, influencing the distribution of galaxies and clusters. Dark energy, the mysterious force driving the accelerated expansion of the universe, also plays a significant role. By studying the CMB and other astronomical data, scientists can infer its properties and impact on cosmic evolution. Innovative methods and interdisciplinary approaches have been crucial in these studies. From machine learning algorithms to international collaborations, these efforts push the boundaries of our knowledge. We highlighted upcoming missions and projects that promise to further our understanding. The Euclid mission, James Webb Space Telescope, and Simon's Observatory are just a few examples of the cutting-edge research on the horizon. Potential breakthroughs in cosmology could revolutionize our understanding of the universe. Direct detection of dark matter, insights into dark energy, and new particles discovered at colliders could all lead to groundbreaking discoveries. Interpreting the vast amounts of data from these missions presents challenges, but also opportunities. Advanced data analysis techniques and continued technological innovation are essential for making sense of our findings. The ongoing quest to understand dark matter and dark energy is a testament to human curiosity and ingenuity. Each new discovery brings us closer to answering fundamental questions about the universe. Thank you for joining us on this journey through the cosmos. If you enjoyed this video, please like and subscribe to our channel. Check out our other videos for more fascinating insights into the mysteries of the universe. Your support helps us continue to bring you high-quality, educational content.